The world we live in is full of life. With a population of 7.5 billion, humans are a minority. Animals outnumber us by far, and there is a lot more than the eye can see. Trillions of microorganisms occupy all parts of the biosphere. They live in, on, and around us. In everyday life, microorganisms can be useful, for example in our digestive system. The human body has a natural defense against microorganisms. However, some microorganisms cause diseases, and if our resistance is weakened, we can become sick. These microorganisms are referred to as pathogens. In a healthcare environment, the maintenance of sterility of the surgical field and medical devices is key in supporting the body's natural defenses. Sterile barrier systems play an essential role in the fight against healthcare-associated infections. They allow medical devices and products to be sterilized and to keep them sterile up to the point of use. A basic requirement for sterile barrier systems is that they have to allow for sterilization of the medical devices in their final packaging configuration. Sterilization may take place within a hospital, at the manufacturer's plant, or may be performed by specialist contractors depending upon the type of product and the sterilization method of choice. In addition, sterile barrier systems, along with their protective packaging, allow sterile medical devices to be safely transported, stored, accurately identified and traced at all times. Maintenance of sterility at all times is critical. Finally, the design of sterile barrier systems must allow aseptic presentation, which means that any risk of recontamination during opening and removal of the sterile product is minimized in order to protect the patient. Validation is a key element in the production and sterilization of medical devices and their sterile barrier systems, and is essential to ensure the safety of patients and users. Validation is a very complex procedure defined by extensive regulations and standards such as ISO and CEN. The definition of validation is confirmation through the provision of objective evidence that the requirements for a specific intended use or application have been fulfilled. Validation is applied throughout design and process stages and to test methods to provide objective evidence. Validation is crucial for sterilization processes and for maintenance of sterility, since there is no effective test to verify sterility before using a sterile device. Sterilization refers to any process that effectively renders a surface, equipment, or article free from viable organisms. The minimum safety level is defined by the SAL, Sterility Assurance Level, of 10 to the -6, which means that within 1 million sterile devices there might be a maximum of one non-sterile product. Medical devices which are intended to be sterilized must have a minimal bioburden, which means the number of microorganisms on the device must be low and consistent. For this reason, medical devices have to be manufactured and packed in an appropriately controlled environment. Terminal sterilization of medical devices can be achieved via a number of technologies. The most common technologies used in the medical industry and in healthcare facilities include heat, commonly using steam or, in some special cases, dry heat. Radiation, typically using gamma rays, electron beam, also called beta rays, and X-ray. Low-temperature gaseous sterilization, which uses many different sterilizing chemicals. The most often used sterilants are ethylene oxide, commonly referred to as EO sterilization, and vaporized hydrogen peroxide. Steam sterilization is commonly used in hospitals and is typically carried out in a sterilizer using steam heated to 121 to 134 degrees Celsius. Steam destroys organisms by coagulating the cell protein and rendering them inactive. Steam sterilization is very effective but can be overly aggressive for some device components or the materials of the sterile barrier system, and cannot be used for heat or water-sensitive materials. Sterile barrier systems must be porous to allow the steam agent to enter the pack and withdrawn after sterilisation. All three radiation technologies, gamma, electron beam and X-ray, are suitable for sterilisation. The main differences are penetration capability and exposure time. Gamma and X-ray have high penetration capabilities and are suitable for large packages and palletized loads. Electron beam irradiation has limited penetration and is more suited to sterilisation of single boxes. Gamma irradiation is generated by the disintegration of cobalt-60, a radioactive isotope. The energy generated causes the death of microorganisms by disruption of the DNA molecule, thus preventing cellular division and propagation of biological life. It requires bulky shielding for the safety of the operators and storage facilities for the cobalt-60, and is generally carried out at a limited number of facilities under contract. Product exposure is typically measured in hours and varies depending on product density, its packaging and strength of the source. Electron beam sterilisation, in the simplest terms, is the bombardment of a material with high-energy electrons. These electrons react with molecules in a material to produce free radicals. Free radicals can induce changes in polymers and disrupt the DNA structure, resulting in sterilisation. Electrons are generated in a vacuum by the source and accelerated by a radial electric field, which transmits energy to them. On exiting the accelerator, the beam of high-energy electrons is guided to the radiation vault and onto the product. High-energy X-rays are similar to gamma rays and disrupt the DNA in the same way. Both are pure energy photon radiation. X-rays start as an E-beam, but after acceleration, the high-energy electrons are directed onto a tantalum plate, which converts them to X-rays directed onto the product. Sterile barrier systems do not need to be porous for irradiation to be effective, but it can have some detrimental effects on certain materials, which can lead to changes to physical and chemical properties. Ethylene oxide sterilisation uses ethylene oxide gas, which is a chemical agent that kills microorganisms by interfering with normal metabolism of protein and reproductive processes, leading to death of cells. Ethylene oxide sterilisation is typically carried out between 30 and 60 degrees Celsius with the relative humidity above 30% and a gas concentration between 200 and 800 milligrams per litre. A complete cycle will take 24 to 36 hours depending on cycle specification. Ethylene oxide sterilisation is commonly used to sterilise devices that are sensitive to temperatures greater than 60 degrees Celsius or are moisture sensitive. The sterile barrier system must be porous to allow the sterilising gas into the pack and be withdrawn after sterilisation. How does a sterile barrier system work? Sterile barrier systems can be made up from a variety of materials depending upon the product to be packed and the sterilisation method. All materials must provide a barrier to microorganisms whilst allowing the sterilant to penetrate. Sterile barrier systems made from non-porous films can only be sterilised by radiation. Porosity is required for gaseous sterilants to penetrate inside the packaging. In this case, the microbial barrier is created by materials behaving like a filter. Air is constantly exchanged through porous materials due to changes in atmospheric air pressure and temperature during transport and storage. Porous sterile barrier systems are designed and manufactured normally from fibers or filaments so as to create a tortuous path with carefully controlled porosity to allow sterilizing gases to penetrate whilst capturing the particles in the tortuous structure. Microorganisms and the particles they are normally attached to are retained in the barrier material based upon a number of filtration mechanisms depending on their size. 3 key filtration mechanisms can be distinguished to remove particles from the airstream. Interception occurs when a filter fibre splits the airstream that a particle is following. If the center line of a trajectory is closer to the fiber than the radius of the particle, it collides with the fiber. Inertial impaction is when a particle, as a result of its mass, deviates from the airstream flowing around a fiber and collides with it. The effectiveness of this method of capture is directly related to the mass of the particle and the speed of the airstream. Diffusion occurs when a particle intercepts with a fiber as a result of random particle movement, Brownian motion, and, for some materials, electrostatic attraction. All three of these mechanisms are in operation at all flow rates and for all particle sizes. However, larger particles moving at higher flow rates are more likely to be trapped by inertial impaction, whereas lighter ones moving at slower speeds are more likely to be caught by diffusion. The design of a sterile barrier system is a carefully considered and tested procedure. Many aspects need to be taken into account. The final design needs to be validated to demonstrate that the requirements for a specific intended use have been met. The sterile barrier system and its materials must be compatible with the chosen sterilization process. It must allow the device to be sterilized and maintain sterility at all times. The protective packaging must protect the device and the sterile barrier system through the hazards of transportation, handling, and storage. The sterile barrier system must also be compatible with the device from a biological and toxicological point of view. The sterile barrier system should also be designed considering the requirements of a variety of packaging machines for forming, sealing, and assembly, and must be compatible with printing and labeling systems. Traceability is essential and must be maintained over the entire manufacturing process so that potential issues can be traced back to their root cause. The final product must allow the end user to clearly identify the medical device and to present it aseptically. Disposal and recycling requirements need also to be taken into consideration. The medical device industry is highly regulated, and as an accessory to the device, sterile barrier systems must comply with recognized national and global standards. Sterile barrier systems are manufactured under rigorous quality management systems to ensure consistency of critical properties subject to customer audits. All sterile barrier materials and systems undergo extensive testing to ensure they're fit for purpose. Seals are carefully tested for strength and integrity. Performance testing will demonstrate that the packaging system, the combination of protective packaging and the sterile barrier system, is able to protect the device through the expected hazards of handling, distribution, and storage. Accelerated aging techniques are used to simulate the aging of packaging to demonstrate that package integrity and microbial barrier properties are maintained over the entire shelf life. The design validation is only complete when it's been demonstrated that after real-time aging, all properties are maintained within defined specification limits. The rigorous design, production control, validation, and test regimes ensure that the functionality of the sterile barrier system is maintained at all times. All parts of the supply chain, from raw material and sterile barrier system manufacturers, medical device manufacturers, sterilizers, and end users work together to protect the patient. We can provide information, guidance, and support on all matters relating to sterile barrier systems, including their design and use. Our website is designed as an educational source and offers guidance on regulatory information and material choice. The website also includes videos explaining various aspects of sterile barrier functionality. Links to our members' websites can also be found for further information and support.